Good day, esteemed researchers and curious minds tuning in from around the globe. We're diving into the fascinating world of AI with our presentation on benchmarking general-purpose in-context learning. This groundbreaking research, led by Fan Wang, Chuan Lin, Yang Chao, and Yu Kang, redefines GPICL, introducing innovative benchmarks that could revolutionize language modeling and indoor navigation. Stay with us as we explore the potential of these benchmarks and the future of AI learning. Let's get started. Our research has taken strides in redefining and enriching the concept of general-purpose in-context learning, or GPICL, highlighting its importance to the AI community. We've introduced two innovative benchmarks, MetaLanguage and MazeWorld, both capable of generating unlimited synthetic data. The MetaLanguage benchmark creates a randomized yet consistent language pattern. This demonstrates a model's potential to learn a new language from scratch, a significant leap in the field of AI. On the other hand, the MazeWorld benchmark generates an infinite number of tasks within randomized mazes. This unique approach trains the model to learn exploration and navigation, pushing the boundaries of what AI can achieve. Our preliminary results are promising. We found that a randomized metalanguage can indeed train a language model. Furthermore, this model can understand realistic natural language to a certain extent. This opens up new possibilities for the application of AI in various fields. Let's delve into the concept of general-purpose in-context learning, or GPICL. This is a topic of great significance to the AI community, as it redefines and enriches our understanding of language learning models. Now consider the current large language models, or LLMs. These models are typically trained on specific, existing languages. However, the complexity of natural language far surpasses the 8-gram model that these LLMs often use. This is illustrated in the figure, which compares the learning pipelines of GPICL and current LLMs. The challenge, therefore, is to develop models that can learn and understand new languages, not just existing ones. This is where our research comes in, and we'll explore this further as we progress. Visual signals in maze worlds present a challenge. They are regularized and relatively monotonic, making them less complex than those found in the real world. This simplicity limits their applicability. Similarly, synthetic data generated by existing benchmarks have not yet been validated for direct application, posing another hurdle. Our focus is on two specific problems. First, we aim to enable models to learn a new language from scratch. Second, we want these models to navigate through mazes. These tasks test the model's ability to learn in context, a crucial aspect of AI development. By addressing these issues, we can push the boundaries of what AI can achieve and open up new avenues for research and application. This is not just about solving a problem, but about expanding our understanding of AI's potential. While previous solutions have offered valuable insights, they've faced limitations such as insufficient complexity and a lack of validation for direct application. To address these issues, we've introduced two novel benchmarks, MetaLanguage and MazeWorld. These benchmarks generate unlimited synthetic data, providing a rich resource for training. MetaLanguage creates a randomized yet consistent language pattern, allowing models to learn a new language from scratch. On the other hand, MazeWorld generates an unlimited number of tasks within randomized mazes, training models to learn exploration and navigation. These benchmarks are not just novel, but they also hold immense potential. They can significantly benefit the research of in-context learning and general-purpose in-context learning, and ultimately advance the field. By generating unlimited synthetic data, they provide a unique opportunity for models to learn new languages and navigate complex mazes. In essence, our approach offers a fresh perspective on the problem, and we believe it will open up new avenues for research in the field. Our research introduces two innovative benchmarks for general-purpose in-context learning, namely meta-language and maze-world. Meta-language is a unique tool that generates new languages to assess the learning capabilities of models. The complexity of the sequences it produces is determined by the formula NN, where N represents the size of the vocabulary. This allows us to control the complexity of the pseudo-language, making it a versatile tool for testing models. On the other hand, maze-world is a benchmark that generates an unlimited number of tasks within randomized mazes. The model is trained solely through context, learning to navigate and explore these mazes. This provides a practical and challenging environment for models to demonstrate their learning abilities. Together, these benchmarks provide a comprehensive and rigorous testing ground for models, pushing the boundaries of in-context learning. Our research focuses on training models using the Noem decay scheduler, which peaks at a learning rate of 10⁻³ after 1,000 steps. The problem we're tackling is unique. We're concentrating on learning a new language as an in-context learning task. However, it's important to note that the synthetic data generated by our benchmarks are not yet validated for direct application. In our experimental design, we use these benchmarks to generate synthetic data for training. We then evaluate the models on their ability to learn this new language and navigate through mazes. Looking ahead, there are several ways to expand this work. We can develop more realistic general-purpose in-context learning benchmarks, adding greater complexity to the meta-language. There's also potential to uncover more sophisticated models and optimization techniques, which could extend the GPICL horizon and enhance performance gains. In summary, our research is a step towards understanding how models can learn new languages and navigate complex environments, and we're excited about the possibilities this opens up for future exploration. Our research has yielded some truly inspiring preliminary results. We've found that a randomized meta-language can effectively train language models to understand realistic language. This has potential applications in areas such as language modeling and indoor navigation. The complexity of the sequences we generate is bounded by NN, and we've trained our models using the Noem decay scheduler. Now, let's consider the implications of these results. They offer potential benefits for in-context learning and general-purpose in-context learning research. Our models have demonstrated the ability to learn new languages from scratch. The benchmarks we've proposed are versatile and broadly applicable. They're scalable and adaptable, making them a valuable tool for future research. This is a significant step forward in our understanding of language learning and AI. Our research has made significant strides in the field of general-purpose in-context learning, or GPICL. We've not only redefined and enriched this concept, but also introduced two novel benchmarks, meta-language and maze-world. The meta-language benchmark is a randomized yet consistent language pattern used for meta-training models. It's designed to generate a vast number of new languages, testing the model's ability to learn an arbitrary new language. On the other hand, maze-world generates an unlimited number of tasks within randomized mazes. Here, the model is trained solely through context to learn exploration and navigation. The figure displayed here evaluates language models of various sizes on the meta-language benchmark with differing levels of complexity. This visual representation underscores the potential of these benchmarks to benefit the research of ICL and GPICL. In conclusion, our work has laid a solid foundation for future research in this field, and we look forward to seeing how these benchmarks will be utilized and developed further.